Hello guys, it's Zungzels here, and today, continuing physics, investigating the mechanics of nature. Now, out of the way, get into it. Chapter 4, Gravity. Why does the Earth orbit the Sun and not the other way around? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, liftoff. We have liftoff of the space shuttle on its way to the International Space Station. Aboard is a team of 5 astronauts, poised to conduct a series of experiments in space. Sending astronauts and equipment into space, the first concern is for safety. But another important thing the NASA or another space agency needs to think about is gravity. Gravity, the attractive force that exists between objects that have mass. In trying to send a spaceship off of the Earth's surface into orbit, we need to overcome its gravity. We need to overcome gravity is virtual. Gravity is everywhere. If you're sitting on a chair, you're sitting in a chair right now with this book resting on your desk, there's gravity at work. The chair has gravity and is pulling on your lower half. And you have gravity and you're pulling on the chair. This book has gravity and is pulling on the desk, while the desk is pulling on the book. Gravitational pull created by each and every massive object reaches throughout space. In fact, the gravitational pull created by our own mass reaches all the way to the edge of the universe. It's very weak, but it's there. Gravity pulls things toward each other. It depends on 2 things, mass and distance. The Earth's gravity is pulling objects toward it at a rate of 9.8 milliseconds. It's a good thing you're standing on the surface. If not, you'll find yourself falling pretty fast. You're falling faster for each passing second until the force of friction experienced from the atmosphere equals the force of gravity. Mass is the amount of matter that makes up an object. You are made of matter. The sun is made of matter. And this book is made of matter. A spaceship has mass. This mass is significantly less than the mass of the Earth. A spaceship has mass. This mass is significantly less than the mass of the Earth. As a result, the Earth has much more gravity than the spaceship. When astronauts blast into space, the gravitational pull of the Earth is trying to keep the spaceship close to home. The spaceship has its own gravitational pull, which is acting on the Earth, but it is too small to measure. Take a look at the planets of our solar system. They are in orbit around the sun. That's because the sun is so massive, its gravitational pull can keep the planets in orbit around it. The sun has a mass of 1.98892 times 10^30 kilograms. This is roughly 99.86% of all the mass in the entire solar system. Mercury, Venus, Earth, and Mars are the inner planets. Jupiter, Saturn, Uranus, and Neptune are the outer ones. The inner planets are smaller and rockier, while the outer ones are giant gas planets. The planet's positions in space are determined by several factors, including temperature and gravity. Gravitational pull of a planet will impact the weight of an object standing on that planet. The terms weight and mass are often confused. Remember, mass is the amount of matter in an object. Weight is a measurement of the amount of gravitational pull pulling on an object. Astronauts on the moon, which has gravitational pull of about 1/6 of the Earth, have the same mass as they do on the Earth. However, the weight will be different. An astronaut and all her gear weighs 690 N on Earth, then your weight on the moon will be about 114 N. However, if her mass on Earth is 155 pounds, then the kilograms, her mass on the moon will be 155 pounds, 670 kilograms. A word about projectile motion. Here's a quick assignment for you. Go outside or into the gym. Or try it in your classroom if your teacher lets you. What happens when you toss a ball up and over your head? That's an easy question, isn't it? It falls down because of gravity. Now throw the ball across the yard or gym. Probably shouldn't do this in the classroom. What happens? The answer isn't quite the same, is it? The ball seems to travel horizontally first, and then gradually fall down, but the ball actually begins to fall immediately. The velocity of the ball in the downward direction starts at 0 when you throw it horizontally. So it takes a moment for the ball to accelerate under the gravity to a velocity our brains can notice. The ball will keep accelerating downward until it hits the ground. See how the ball makes an arc? In physics, the ball is called a projectile. A projectile is the object that is thrown. In motion, the project is called projectile motion. The ball is thrown with some force. You are trying to get it across the yard. The gravity takes over and pulls it toward the ground. There are many times when the projectile motion of an object must be considered. When a pitcher throws the ball across the home plate, when the quarterback makes a pass, or when a tennis player hits the ball across the net. That's so relative. Are the laws of gravity are the same everywhere, even in deep space? In 1905, Einstein's theory that the laws of physics, including Newton's laws, were the same. Any observer who is not celebrating Einstein is famous for the equation E equals mc2. States energy, E, is equal to mass times the speed of light squared. This means that the energy concept and the mass concept in an object are directly potential to each other. These ideas make up what is known as Einstein's theory of special relativity. Einstein also wanted to address the idea of acceleration in 1915. He published the theory of general relativity. This theory helped explain what he was looking for. Einstein theorized that massive objects such as stars create distortion in space. This distortion is felt as gravity. For example, the light around a really massive object in space, such as a black hole, appears to bend. This is the gravitational pull of the massive object warping space and time. Therefore, redirecting the light closer to home. The orbit of Mercury, the planet closest to the Sun, is changing ever so slightly. And because of the impact Sun's gravity is having on space and time. In a few billion years, Mercury will be on a collision course with Earth. And that's it for today, guys. Hope you guys enjoyed. And see you again very, very soon. Later.